Thank you so much, Amber. Thanks, folks, for coming on in. As Amber mentioned, this is a bit of a longer form discussion of the like 15 or minute talk I gave at AICHE on convective heat transfer. And it's kind of a continuation of the paper we wrote earlier this year on the same topic. This is a really interesting topic because it really shows the utility of a tool like LBM for solving turbulent convective transport processes and how we can access certain physics, in this case, energy dissipation rates and near wall behavior that elucidates a process and generalizes a process that was previously, I'd say, very correlation driven. So again, this is the paper we'll be speaking to throughout the day that I invite you to reference after the fact. And we'll talk again pretty simply with some theoretical background, implementation, validation, next steps. I don't even know why I put the agenda slide up there. Every talk follows this agenda, but nonetheless, there it is. But more importantly, please keep in mind that this paper does exist and it talks about these things in line by line detail. Just to kind of some umbrella statements here, who M-Star is and what we're trying to do here. M-Star is a software company that develops physics-based modeling tools. We want to develop first principles modeling tools for scientists and engineers, and our goal is to generate models and create data that is functionally indistinguishable from measured data. I know that's a tall order. That's kind of a North Star where we're trying to go, but that's what we're trying to get. We're not a correlation house. We're not trying to create, tools for looking up data. We're not trying to create tools that predict, just a mean flow field. We're trying to predict time accurate three-dimensional flow physics that compare immediately to what might be measured inside of a lab. So again, when I say time accurate three-dimensional, I mean things like this. Here we have a process when we're adding some sort of secondary fluid to this agitated vessel. There's the free surface. Here we're cutting a plane through to look at the velocity. Here are some of the EDR and the trailing vortex, as it were. Here's the blending of that dye as it moves throughout the vessel. Importantly, what we're predicting here is directly analogous to what you'd see or measure inside the lab in terms of the time evolution of the velocity field, or maybe perhaps the time evolution of the concentration of the species as homogenized through the tank, and comparing how the conductivity, for example, varies across three different probes as they converge towards a well-stirred state. Or if we have some PIV measurements or whatnot, trying to characterize EDR or shear in trailing vortex, we want to predict data as it evolves in real time. Here's a bit more of a cheeky example, looking at just a jellyfish kind of move through fluid. But again, this is what we're trying to get at here, is time-accurate three-dimensional process simulations that allow us to build what we might loosely call digital twins of an actual physical system. Key differentiator, M-Star is born and bred to run on GPUs. I'll be talking a bit about GPUs today. And that GPU basis allows us to run routinely orders of magnitude faster than the conventional CPU-based code. And that doesn't just mean we run the same old stuff faster. It means we can attract problems and challenge problems that were previously intractable in a practical industrial sense. How we think about simulation, as I mentioned, we are trying to drive the problem towards more foundational physics. I speak to this slide in most of these seminars. We have new people each time, so I'm just going to highlight it one more time. A lot of engineers operate in correlations. We're going to be talking about correlations today. They serve as a pretty useful foundation for a lot of engineering. Correlations are great. Correlations are quick. Correlations can be very accurate, but correlations tend to be pretty specific, right? Like the Nusselt number of flow over a sphere is related to the Reynolds number and the Prandtl number. If you don't have a sphere, this isn't applicable, right? If you're not within the regime in which this correlation is parameterized, it's not applicable. So they're very good, but they're very specific, as it were. Below this, we have continuum representations, things like Navier-Stokes, things like advection diffusion. These are great modeling tools that allow us to reconstruct correlations. Below that, we have actual transport carriers. We're modeling eddies, we're modeling particles, bubbles, etc. This is where we try to live. We try to model systems at the level of the transport carrier, broaching into the continuum in an effort to understand the physics driving process outcomes, and if necessary, develop correlations that can be used for faster calculations. But foundationally, we're living down here, and the introduction of GPUs as a computing paradigm allow us to push away from correlations with a little bit of continuum down to continuum with some transport carrier physics, which allow us to create more general, mechanistically consistent modeling approaches. So again, in this little agitated vessel here, I've shown this before, we've got some CFD DEM simulation. We're agitated in a slurry. We have a free surface there. Importantly, we're not using a mean velocity field coupled with like some sort of like correlation to predict, whether or not the particles are going to get off the bottom of the tank. Now, we're not using a correlation to predict, say, a vortex depth as this unbaffled system is agitated. We're actually modeling the Navier-Stokes equations and the trans-Navier-Stokes equations in real time. We're actually tracking all these individual particles as they move throughout the vessel. And so we're not using correlations to predict the physics. We're modeling the physics at the level of the fluid and particle mechanics in a way that we can reproduce what we measured experimentally and corroborate possible correlations that might exist. For example, we're not going to say, oh, well, we're not going to say, oh, you've got this operating condition. Well, let's look up Zwittering and predict whether or not you're going to get particles suspended. We're going to model the actual physics and compare against either measured data or some of those off-the-shelf correlations. This is made possible by GPUs. I'll speak to this point with a new slide. Again, just to kind of keep everyone on the same page, GPUs are incredibly dense compute architectures. In contrast to CPUs, which might have 4, 8, or maybe 16 compute elements or algebraic logic units, a CPU will have thousands. A GPU will have thousands or tens of thousands of these logic units. This allows for massive parallel computing. Furthermore, GPUs have all the memory they need on the accelerator, on this chip itself. So unlike a CPU, which has to, and the CPU is under the heatsink, unlike the CPU, which has to go through the motherboard, through the PCI to the RAM, and go bring it back to the algebraic logic unit in order to do math, the GPU has all the memory on the chip directly. So what you're looking at here, this is the GPU. There's the heat sink and cooler. Underneath this thing is the actual the logic unit and the memory. But to be sure, all of it's local, which makes memory bandwidth very, very high on a GPU. Further, order of magnitude higher than trying to travel through the PCI bus. Furthermore, the compute density means that a standard GPU can do math, an order of magnitude faster than a standard CPU, even with multiple cores. And the net effect of these higher memory bandwidth and compute speed is that one GPU, when doing dense, I'd say nearest neighbor math, can operate at the same speed of several hundred CPUs. Okay, so the net effect here is that one good GPU can advance through physics about 400, 500, 300, some hundreds of times faster than that single chipset might. And again, that's what's making this possible in terms of today, us being able to routinely run these 100 million grid point simulations or 100 million DEM particle simulations at industrial scale in hours or days, or even less than that, because these GPUs present such a step change in how in terms of the compute density offered to us as simulators. So again, we're not going back. In fact, M-Star, we don't even run on CPUs anymore. There's no point. Okay, running on a CPU is like running on leaded gas. It's like I don't even think it's selling anymore, of course, but it's kind of like it's a trick. It's novelty at this point. Moving forward, it's all about the GPUs. And I'll speak to that point more aggressively with this kind of idea here. A couple points on this. This kind of GPU paradigm, just kind of step back here, really came to bear about 15 years ago. I remember reading this article, and it really piqued my interest. How the Air Force in 2009 and up into 2010 started amassing PlayStations because they recognized that the GPUs on them had tremendous compute capacity. Okay, so they go and buy 1,800 of them, and they connect them to make one supercomputer built on these GPU cards that were in the PlayStations. Because the GPU is nothing more than a graphics processing unit. It communicates to a monitor what sort of color ratios, red, green, blue, it should show at each pixel. So a GPU is a pretty simple graphics rendering object, but it has some compute functionality. And what the Air Force did here is they said, listen, if we just use GPUs, we can build a computer, one of the fastest on the planet, for pennies on the dollar, right? Like 1,800 PlayStations is a lot, but it's not a lot when you're trying to build the 33rd fastest computer in the world. Realistically, a coordinated stop to Walmart allowed them to build what was a phenomenal research hardware. And that kind of got some interest in the community saying, oh, wait, we know these kind of GPU hardwares exist. We thought of them as kind of gaming tools and whatnot, but wait, they're actually compute elements. They can actually do something. They can actually do math. And if you write code to run on these things, they can do phenomenal volumes of math, as it were. And what's interesting here is that NVIDIA, which is kind of the primary manufacturer of GPUs throughout the 90s into the aughts and whatnot, they caught wind of this, of course. And then in 2012, they started releasing GPUs just for scientific calculations. And what I mean by that is this was the K10, one of their first kind of scientific computational physics GPU. And what's unique about it is it has no monitor port. Okay, like that's kind of like absurd. It's kind of like it blows your brain, but then it doesn't. It's like, oh yeah, there's no place to plug your monitor into the GPU. Of course not. We're not for just display anymore. I think it's kind of funny. If you look at the end of it, it's just the fan. And so like suddenly we've kind of jumped the shark on what a GPU is. Like it's not even doing any graphics help anymore. It's pure math. And we know the story after this. So it's I'm not selling NVIDIA stock here. I don't own any individual stocks. Either way, but foundationally, Intel dominant player. Here's their market capitalization. NVIDIA order of magnitude smaller. They roll out some of these scientific GPUs, machine learning, AI, big data come into play, and 15 years later, they're over 2 orders of magnitude larger in size. Like this market cap is a semi-log plot. Okay, they become orders of magnitude bigger, orders of magnitude bigger than Intel even. And again, a lot of this is driven by kind of AI and whatnot, which is fueled by GPUs. But it's kind of a really cool, like somewhere at some business school, they got to teach this case about how technology originally developed for games and first-person shooter games was demonstrated by a research lab to have extreme computational efficiency. And so a company then recognized, what, we can sell these things. Let's get rid of the graphics port, make them just for scientific computing, and watch what happens. And yeah, something cool happened. So at the end of the day, when M-Star was founded, we saw this. We wrote immediately for the GPUs, and we haven't looked back since. So importantly, this sort of GPU native approach motivates the types of physics we solve, because not every algorithm can just be run on a GPU. You need to be able to solve a physics problem that can operate well in these architectures. So when we're solving fluid mechanics, we're solving the transient Stokes equations, we're doing DNS and LES, and we're using LBM, because that's the most efficient way to solve these problems in a GPU. When we're using, when we're doing species transport, we're solving the transit advection diffusion equation, and we're using these nearest neighbor LBM and or finite volume schemes. We're not going to solve a large banded matrix. We're going to be solving and using, I should say, nearest neighbor compute dense approaches. We're doing particle transport. We're going to track, whenever possible, every particle. And if we need to calculate nearest neighbor list or whatnot, we'll use BVH trees, objects that structure very well on GPUs. So again, because we're wedded to these architectures, we choose algorithms that run well on them. Okay, so that's my background. Let's get into kind of the applications to heat transfer now, and how we can use these more modern modeling approaches, more modern architectures to attack physics at a more foundational level, particularly in the area of heat transfer. Okay, we're going to make a pivot here, but I'm going to start talking about some heat transfer mechanics, and I'm going to appeal to some of these kind of more foundational modeling approaches as I go through it. Convection is a big problem within the context of mechanical and chemical engineering, but I think that we've honestly reduced ourselves into how we think about these problems. When we are taught convection, and we think about modeling convection within any sort of transport physics 101 class, we almost always start by appealing to a laminar boundary layer. We say, ooh, look, if we non-dimensionalize transport through this boundary layer, we can recover this sort of non-dimensional Nusselt number as a function of Reynolds number and Prandtl. And this is great. You can derive these quantities directly from laminar flow theory, and you can derive this relationship between conduction, Reynolds, and Prandtl. There is an exact solution to this for laminar flows, which allows us to predict what sort of non-dimensional heat conduction we're going to get, that's Nusselt, as a function of flow velocity as encapsulated in Reynolds, and this ratio of thermal transport to momentum transport encapsulated in Prandtl. So because there are some exact solutions in laminar flow to flow through a cylinder or whatnot, whether it be both an average or local, this is recognized as a victory of laminar boundary layer theory. And because it falls directly out of non-dimensionalizing these convective mass transfer equations, we almost treat them as somewhat sacrosanct. Like we have some sort of Nusselt number, Reynolds, Prandtl. Like this kind of trifecta, this trinity of non-dimensional parameters is what we use to describe convection. And because it works so well in laminar boundary layer theory, we kind of apply it everywhere. You've got flow over a bank of tubes and you want to predict what the convective heat transfer coefficient? Good news. We got 3 dimensionless groupings for you. Reynolds, Prandtl, Nusselt. Fit it to that. You've got flow over a wedge that's tumbling. Good news. Throw Reynolds, Nusselt, and Prandtl on it, and you'll develop some correlation that links those 3. And that's not a problem, but it's kind of glossing over a lot of the physics. Said again, yes, I know, hand to heart, that if we look at laminar boundary layer theory, we can arrive at this real cool correlation between Nusselt, Reynolds, and Prandtl and find exact solutions. But then for us to say that all problems must collapse onto this 3-dimensional design space, maybe introduce a few more dimensions of viscosity ratio or other sorts of system-specific dimensionless parameters, but to say that these become the be-all and end-all for describing transport is a bit misleading. Not only because, well, you can fit anything to a 3-parameter fit, but also because they're masking a lot of the physics. Okay, like sure, I love this correlation. This is super handy for predicting flow over a bank of tubes. But pray tell me, like, how do you come up with this stuff? Like, I remember as a undergraduate student seeing these things and being like, oh my gosh, these are the smartest people in the world. And they're brilliant, don't get me wrong. Like, look at all the math they're doing. But look at how they figured out that the Reynolds number needed divided by 282,000. Like, that's amazing calculus. Like, it's not anymore. And that's not a bad thing. It's just a fit. And that's not a bad thing, but we've really washed out a lot of physics as we take increasingly complicated topologies and shoehorn them in through Nusselt, Reynolds, Prandtl. It's not a bad thing, but why, physically speaking, is that 282,000 to the 5/8? Okay, why? Because it fit. And that's not a bad thing, but admittedly, we've kind of lost sight of the physics and kind of focused on fit and exercise, which is useful. These run quickly, but we've really jumped the shark, motivated by a good origin story. We've started applying these things to everything as Nusselt, Reynolds, and Prandtl, and it works, but we've lost a lot of the physics in the process. So is there a more general way to do this that doesn't lose all the physics, but retains some of the generality of these approaches? And the answer is yes, but you've got to take grad level transfer to get there. So this is not a here, let me show this here. Like this is not like a me thing. Like you open up any sort of like, Hayes and Crawford, or any sort of, more advanced convective heat transfer textbook, and they'll present a more general roadmap that makes a more direct appeal to boundary layer theory to describe convection. It doesn't just get caught up in the trinity of Nusselt, Prandtl, which is great. I love it. But to be sure, like those are humans' constructs. There's got to be some sort of physical origin story that we can appeal to that describes convection across a broader range of systems without appealing to these non-dimensional parameters. And people have done this for decades. We know now. I'll use the pronoun we liberally. People far smarter than me recognized that we could describe conduction across this turbulent boundary layer as a function of a molecular thermal conductivity and a turbulent thermal conductivity that is coming from the fluctuations in this boundary layer. Okay, we know that this turbulent conductivity is going to be related to these transversal velocity fluctuations in the sublayer times the distance they travel. Okay, so we know that if there is some sort of turbulent flow inside this boundary layer, we can relate the rate at which energy, momentum, species, etc., moves through this boundary layer to these fluctuations in the direction perpendicular to the wall and the distance they travel. We know from turbulence theory that we can relate these fluctuations to this friction velocity at the wall, as it were, as well as some dimensionless boundary layer thickness. This nu, that's just dimensionless thickness. That's just position within the boundary layer. So think of this as being position divided by delta. I don't have that here, but that's what it is. And so we know, for example, that these particular distance they travel is likewise related to the boundary layer thickness. And so we have these kind of core principles that allow us to say, as a function of the local fluid properties at this point in space, we know, or rather have a pretty good authority that the convective heat the heat transfer rate should be a function of the molecular conductivity or molecular diffusivity mass transfer, as well as this turbulent component, as it were, where it's dependent on the boundary layer thickness, the friction velocity, and some non-dimensional position within the boundary layer. We can integrate this term here across the entire boundary layer to arrive at some general expression. Again, it's in Kayes and Crawford. It's in the general literature. You can find there every 10 years, someone resurrects this idea and rederives it and applies it to some system. But to be sure, there is some sort of general relationship for the local convective heat transfer coefficient along some patch of solid in turbulent flow that's a function of some scaling factor, some Prandtl number, some viscosity, some friction velocity, and some boundary layer thickness. If we knew these quantities, we could then calculate what the convective heat transfer coefficient should be, or mass transfer, over that particular patch of solid interacting with turbulent flow. We have very good expectations on what the boundary layer thickness should be as a function of the velocity and the fluid friction velocity. Likewise, we have very good authority that tells us that the fluid friction velocity should be related to the energy dissipation rate. And so if we combine these guys, we can arrive, and again, this is in Kayes and Crawford, this is in other literature, we should be able to arrive at this expression for local convective heat transfer as a function of the local fluid properties. And it should be a function of some sort of Prandtl number, some ratio of thermal diffusivity viscosity, some energy dissipation rate along that patch of wall, and the fluid viscosity. So again, this is not a John Thomas thing. This is not an M-Star thing. This is a general semi-empirical expectation. It's semi-empirical because some of these parameters are in fact semi-empirical. But so that leaves some ambiguity what the cofactor should be, whether it should be 0.2, 0.3, 0.15. And the Prandtl number as well, should it be 2/3, 3/4? There is a little bit of ambiguity in the cofactor because there is some semi-empirical ingredient. But to be sure, this idea that we can relate the local convective heat transfer over some patch of solid to the local energy dissipation rate and the local fluid properties, that's grounded. That's based, as it were. And what's neat about this is not appealing to a Reynolds number. Like, we don't have to add this human-derived Reynolds number in order to calculate H, which makes sense. Because if I'm looking at a patch of wall and trying to predict convective heat transfer from that patch of wall, the fluid and the solid patch don't stop and think, oh, wait, what was our system length scale? What was our Reynolds number before they transfer thermal energy? All the information the fluid needs to move energy from the wall into the fluid is contained in that fluid, right? And that relevant piece of information, as evidenced by these first principles models, or I should say semi-empirical, is the EDR, the viscosity, and the Prandtl number, which is just the rate, which is material properties, as it were. These are really cool. This is kind of a cool idea. Now, why is this? Why have we not littered the world with these correlations? Well, why is this not the first thing you learn when doing convective heat transfer modeling? Well, it's because energy dissipation is, generally speaking, a hard thing to calculate. Like, unless we have a well-defined system, we may not know the energy dissipation at the wall, right? We may know the energy dissipation across the system. Like, we could look at, say, a flow over a bank of tubes. We know the pressure drop and flow, which gives us power in. The first law requires that's related to power dissipation. So we can calculate the average power dissipation in the system and maybe use that, but that doesn't work very well. We really, really need the energy dissipation along the wall to make this correlation work, right? We need to know what the EDR is adjacent to the boundary layer in order to use these boundary layer theories to properly predict convective mass transfer, heat transfer. But that's where something like M-Star can come in, or LBM, I should say. So tools like LBM are very good at predicting energy dissipation rates, okay? Both global and local. These are validated very well against looking at EDR inside trailing vortices or comparing energy system level energy dissipation rates to system power input rates and corroborating the first law. So what this looks like here is we can say, okay, we can choose kind of what we think is a semi-empirical correlation, and I speak in the paper to which one I think is most appropriate. And then along the points of this wall, at each point in this wall, we can calculate what the local convective heat transfer coefficient will be as a function of the EDR incident on that wall. We can then use that convective heat transfer with the local temperature difference to calculate the local heat flux on a point-by-point basis into the fluid. And once it's in the fluid, it becomes a standard mixing problem, which is where we've spoken about that at length for hours in our previous seminars. But here's the point: is like this is how this works. Is we have this map between H and EDR, okay? And using this map, we can then predict how things like H vary along the vessel wall in response to the EDR at the vessel wall, okay? EDR, of course, coming from the velocity field. Well, EDR coming from the strain field, coming from the velocity field, of course. And so the roadmap is this. We predict the time evolving flow field, we calculate E along the wall, and then we just map E to H, right? We can integrate over the entire surface if we want to predict some surface average or surface total H, but in reality, we have the local values. And what we can do then is compare. How does this generalized framework do in predicting convective heat transfer against measured data? So there are measured data points for, say, vessels like this. And why I like starting with a vessel like this is because it presents such a heterogeneous flow field. Like there are regions near the top of the vessel where the convective heat transfer coefficient will be orders of magnitude smaller than what we'll see in the trailing vortex, okay? So if we're going to really test this semi-empirical approach, it better be able to work in a system with large variations in H and EDR. So if we can get this right, it gives us confidence that we can get more, well, even simpler systems moving forward. And so foundationally, here, for example, is a standard off-the-shelf correlation for predicting Nusselt number. We're not using this in M-Star, but we're going to use it as the comparison, because it's very well validated, as the comparison against what we're predicting using this semi-empirical first principles approach. This is a system-level correlation. In M-Star, we have the local by local variation. We then can calculate and recover and integrate to predict the total system-level response, but we're arriving at that system-level response by analyzing the discrete behavior as opposed to jumping straight to the system-level behavior as would be done in a correlation. That's okay, the correlation is great. But let's see how well this kind of general approach sticks up in these very spatially varying systems. Here I'm looking at two different impeller types, a pitch blade and a Rushton. I'm looking at different impeller speeds, as it were, for each of these impeller types. And here I'm looking at the total convective heat transfer coefficient at the bottom of the tank, as well as the vessel side walls. So they're going to have very different total convective heat transfer coefficients, or Nusselt numbers, I should say, because they have very different interactions with the trailing vortex. And what I can see here is using a few different first principles models. Now I'll talk about later which one's best, because there are some arguments over which cofactors are better based on what semi-empirical theory you appeal to. But foundationally, what I can see is that whether it's the side wall shown in red or the dish bottom shown in black, black and gray, my experiment data shown in solid is nailing, or rather my simulation is always containing that measured data, even as I go from convective heat transfer coefficient 2,000 to 12,000, whether looking at the bottom of the tank or the side of the tank, whether I have a Rushton or a pitch blade impeller, I can consistently predict the spatial variation that is bottom versus side wall, and the effects of impeller type and the effects of impeller agitation speed on these convective heat transfer coefficients. And what's neat about this, guys, is there is no retuning going on here. Like I'm not like tuning a knob in the theory in order to make sure that we increase our convective heat transfer coefficient by a factor of 6, as it were. This increase, which matches what is being measured, is falling out of the operation of the model. Said again, the increase in impeller speed, which increases the energy dissipation rate, which increases the local convective heat transfer coefficient, which increases the total Nusselt number. We're not futzing around with things as we change speeds. That's falling organically out of the machinations of the simulation. And to be able to reliably predict its behavior across such a wide range of operating conditions is a very compelling first shot across the bow, speaking to the generality of this modeling approach. Furthermore, we can see this converges very well with the simulation resolution. So here is me, for example, illustrating what I mean by the first law. So again, M-Star does a good job, and I should say LBM does a good job of conserving energy. Power in equals power out. And that's your first step in reliably predicting energy dissipation rate for a convective wall transfer model. Said again, if you're not bookkeeping energy dissipation, you're not going to be able to reliably use an EDR-dependent relationship to predict convective heat transfer. And so foundationally across the board, we can do a good job of matching power in equals power out. And happily, power in agrees with measured power number data, corroborating that the simulation is having a good handshake. As I increase the resolution, and this is common in M-Star, eventually my power converges to a grid independent value. Okay, that is, as the resolution improves and I'm getting a better and better description of this overall flow field, I can get to a point where increasing the resolution does not enhance the quality of my EDR prediction anymore. Okay, and this transition happens right as you start to cross from the Taylor scale and start to approach the Kolmogorov scale. We're not all the way down to the Kolmogorov scale, this LES, but once we get past Taylor, this starts to converge pretty well. And happily, lo and behold, as our power converges, so do our convective heat transfer coefficients. And so at the end of the day, at about the same resolution, where where our energy balance stops changing with resolution, at that point we stop seeing significant changes in our near wall boundary layer transport, as it were. And again, I speak to this a little more in this in the paper, and there's some kind of discussion on why this is, like why things converge the way they do, and that's we can have a discussion after the fact. But to be sure, there is, I think, some good theory based on intrinsic turbulent length scales that motivate this observed convergence behavior in LES simulation. What's interesting, though, is that this idea that we could use energy dissipation to predict, remember I mentioned this kind of gets resurrected every 10 years. This was published 45 years ago. So like years ago, people were understanding this. They just couldn't do it in the simulation context. But years ago, we had researchers that were developing convective heat transfer coefficients using the trinity of Nusselt, Prandtl, Reynolds to predict a impeller-specific convective heat transfer coefficient for a vessel. Okay, and they're like, you know what? This works pretty well. And then they're like, but you know what? We can actually do more. Like we can also use physical properties of the fluid and the power consumption unit volume, irrespective of impeller type, to predict convective heat transfer. So even 45 years ago, they're like, wait a minute. We know this this theory exists. We know in accident vessels, we know what the energy dissipation rate should be incident on the wall. I wonder if this works. And the answer was it did. And so, well, I'm not claiming to have invented anything new. I'm just showing what these guys do in an experiment, we can now do in simulation. I said again, yeah, they did their hand over heart Trinitarian link between Nusselt, Reynolds, and Prandtl, and it works great. I have no problem with it. The only problem I have is you have to do one of these for every single impeller type, and it's kind of lost the physics, as it were. Like, why is that 0.54? Because I told you so. That's why it is. Why is that 0.47? Stop asking questions. It is what it is. And so foundation, it's useful, but it's specific. What these guys did is like, listen. We know that, this is Nusselt, that's Prandtl, and that's energy dissipation rate, and that's viscosity. This is nothing more than just like that same correlation I showed. But like, if we take all of our data from every impeller and use the power per unit volume as a surrogate for EDR, near wall EDR, look at this, folks. We can get one correlation to rule them all. And look at that. They're varying here 6 orders of magnitude, as it were, in terms of these particular energy dissipation rates, and 2 orders of magnitude in Nusselt number. And they're kind of saying here, the constant C for the anchor, blah, 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 blah. The measurements are also fitted with the standard deviation 8% to a relationship available in the literature, 16. Pick your poison. Whether it should be 0.16 and 2/3 or 0.25 and 3/4. You're squeezing a balloon. They're all within 20% of each other. But the measurements also fit the standard deviation 8% to relation available in the literature, which contains only the physical properties and the specific power consumption, i.e., irrespective of the impeller type. Okay, so we've had whispers that this idea is valid, that we should be able to appeal to first principles fluid properties to predict EDR. It just hasn't taken, I think, so much flight because these things are so mother and apple pie. I've got this nice view. We nail results, but as soon as you step out of the bounds, this doesn't become valid. And so if you have more generalized approaches, they do become valid. Is what we're appealing to today. It's just interesting. So, if this approach is general, well, let's apply it to more complex topology. Sure, like general should mean general. Let's look at flow over a cylinder, or flow through tube bundles, as it were. Like, if we believe this is true, as it were, it should work for these systems too, okay? And let's do that. And there are literature correlations. These literature correlations, I'm not using them in M-Star. We're not using them in a model. We're using them as a validation case. We're going to be using the actually mechanistic approach here that appeals to local properties to predict a local convective heat transfer coefficient. We can then aggregate that over the entire system to predict the system level response as predicted from these off-the-shelf correlations. Like I said, these are great. These are fine. A undergraduate me was phenomenally impressed with the minds that created these, and I still am. They're amazing, but foundationally, they're fits. And like I said, what is the physics driving 282,000? Stop asking questions. And so foundationally, we can do some kind of sanity checks. Like, okay, like even before we get any further, like, do we get the simple stuff right? Like, are we in fact correctly predicting, say, drag and shedding frequency? Like, even before we get to convective heat transfer, you got to make sure you're getting the simple stuff right. And yes, we can get the right Struhal number as a function of Reynolds number. We can get the correct drag. I'll speak to that momentarily. So just as kind of like a side note, before you go predicting convection, you better make sure you get the simple stuff right, whether it be power numbers out of a vessel or drag over a tube bundle or Struhal shedding frequency. And we check that box routinely. But let's get to the more interesting stuff here. So here I am, that same semi-empirical boundary layer convective wall model applied to single cylinders, aligned tubes, staggered tubes. I have the experimental correlation with the associated uncertainty, the simulation. Consistently, we can get within that measured values uncertainty. And again, this was the same stinking correlation for semi-empirical theory I use for the isolated vessels, right? And why does it work? Why is it topology and operating condition agnostic? Because it's not appealing to topology or operating condition. All it's appealing to is the local turbulent physics surrounding each individual patch of wall, okay? And that semi-empirical model doesn't care what color the agitator was. It doesn't care whether that was on the back side of a tube or the front side of a tube. And again, same rules of the road apply. We converge with respect to energy dissipation and converge with respect to H with increasing resolution. Importantly, and this is where I spoke to this point of validation, is we can also see a nice handshake between measured data and power dissipation. Said again, we can confirm that the pressure drop on the bundle of tubes is consistent with the force on the tubes, is consistent with the power dissipation, as it were. We're over about 20%, so maybe I do need a little more resolution, but it's consistent with the design correlation pressure drop. We can see, again, we're not just getting, let me put it this way. We're anchoring this to measured data, okay? We're not just using EDRs at face value. We always go back and say, okay, is this EDR reasonable? That is this power dissipation reasonable as compared to the power coming into the system, okay? And that power coming into the system can be measured as well as predicted from literature correlations for pressure drop. We can do this for pipes. Like I said, general should mean general, right? Like even inside a turbulent pipe, if I have a patch of fluid, as it were, like that patch of fluid should have the same sensitivity to heat transfer and boundary layer dynamics as encapsulated by the energy dissipation rate and these thermophysical properties. This was a pretty cool simulation. I ran it on NVIDIA DGX. So this was a 16 billion DNS simulation of a 1 meter long, 10 centimeter pipe. I think that's kind of cool because when you read about DNS or these kind of simulations, like they're usually doing like little like tiny things. Here, I did DNS in a simulation in a system so big you couldn't hold it. Okay, and I think that's kind of cool. It's neat to do like industrial scale DNS. Okay, but to be sure, we can then recover some slam dunk things. We should be able to recover the velocity profile across the center line. We should be able to see the transition from integral to buffer to sublayer as we increase the resolution here. And here was me kind of dipping into this viscous sublayer as I went to my monster simulation at these the resolution 1000 was 16 billion grid points, as it were. And this is kind of cool. It's actually neat to see the code recover. It's not unexpected. It's like, don't fax the Nobel Committee quite yet that, oh, good news, the near wall boundary layer theory is still true. But it's neat to corroborate that. But I think it's kind of cool is to use a simulation to corroborate that in a real industrial scale system. I think it's kind of neat. It did take an industrial scale computer. Thanks to NVIDIA for letting me use their DGX, because this was I think it was like 72 GPUs. But either way, it was kind of neat to see. Okay, let's carry on though. Again, the same logic applies. Like here it is again. Guess who? It's same old familiar. My same convective heat transfer correlation, as it were, that's occurring on a patch by patch basis along this wall. And I can see, again, there is literature values. I'm not using this value in the code. I'm not using the correlation in the code. This is just a standalone literature correlation for predicting convective heat transfer coefficient in turbulent pipe flow. It's a function of roughness and other sorts of physical properties, as it were. And why is it 12.7? Don't ask. It is because it is. And that's fine. I'm not dumping. I'm just saying, like, it's physical, but it's kind of divorced from the physics. And so foundationally, this is all physics. It's semi-empirical, but it's immediately linked to what's going on inside the boundary layer. And what do we see again? An experiment, we know how this convective heat transfer coefficient varies function of velocity. And within the simulation, even with a surprisingly robust range of resolutions, we can nail it using one correlation to rule them all. And this is kind of like the real kind of money shot here. This is all of the stuff I've been speaking about so far, and even some others. Pipes, agitated vessels, cylinders and crossflow, bundles, coils. For all of these systems, there are kind of a dozen off-the-shelf correlations that are, long with lots of cofactors for predicting a convective heat transfer coefficient or a Nusselt number. And that's great. God bless them. But the fact that there's like a dozen of them illustrates the problem. Is like whenever you got a system, you better derive a correlation for it. In the simulation, I have one to rule them all. One that's appealing to local turbulent physics, as it were. One that's describing local convection as a function of local fluid properties, EDR, and other sorts of thermophysical properties, specifically viscosity and thermal diffusivity. And the mapping between the two, regardless of topology, consistently within 30%. Okay, and that's not bad considering the correlation uncertainties are typically 20 to 30%, as it were, on a good day. And so foundation, the fact that we can reproduce this across 2 orders of magnitude of H is pretty cool and speaks to the generality of this turbulence theory. And again, I'm not kind of trying to say that we've discovered new science. This has been around for decades. It's cropped up even 45 years ago. People were alluding to this fact. What I'm saying, though, is that when we can run simulations that can reliably predict physics near the boundary layer, specifically EDR, it allows us to go back in time and appeal to some of these more foundational approaches and show A, that we're right, and B, they have extreme utility within some of these more modeling approaches. We can validate this more directly as well. This is again borrowing a bit from some work done by SPX Flow. Big shout out to SPX for helping us with some of these measurements. I think we have some folks on the call here. I don't know, but reach out to them. A great guy to reach out to SPX is Ben Boyer. I just say him. He's just anonymously. He's someone you can reach out to. People you should reach out to that did this data. They're very, very good at this. And also, there's lots of them, but yeah, either way. But foundationally, we can also like do this in industrial scale and validate it. And so we've got all the simulation, all this correlation. Let's just measure the darn thing, as it were. Okay, so here is, for example, just a jacket and a shell system. So we've got some sort of jacket with hot oil going through it that is going to be conducting through the jacket, conducting through the shell, and then transferring thermal energy into the fluid, okay? I'm going to define a few kind of like housekeeping items here. I'm going to call this the shell side. Okay, that's the heat transfer inside the shell. I'm going to define the jacket side, and I'm going to define the process side. Now, when we're talking about temperature, the process side and the jacket side is very similar because this shell is pretty thin. But to be sure, there are 2 different points here. When I speak about the jacket side, there is a different temperature in there. The oil inside this jacket will have a different temperature than the oil inside the shell. Yes, as time goes on, eventually this process side temperature will converge to a value consistent with that of the jacket minus the conductive losses. But to be sure, we just want to get that nomenclature clear. And so we have measured data for this, as it were. We know what the jacket looks like. We know what the flow rate is. We know what the properties of this oil coming through it might be. We know what kind of impeller we have. We know where the temperature probes are. We know everything about the system, as it were. And so we can then measure how this behaves over time. So we can't in an experiment though see inside the jacket, but that's where simulations start to become useful. So here is, for example, what the velocity and temperature look like inside that jacket. And again, I haven't validated this because we haven't measured this, but I'll show you how we can validate the overall system response, which corroborates this result here. So again, I'm foreshadowing here. We wouldn't get the overall system right if we got the jacket wrong. Okay, it's indirect validation, but compelling nonetheless. So this is, for example, the time evolution of the temperature inside the jacket. We have this hot oil coming in. I'll play this again. This hot oil moves through the jacket. Then we have a few degrees cooler oil on this back side and eventually exiting this particular jacket. So hot coming in, cool going out, comparatively cool going out. And this is the temperature variation across that jacket. This temperature variation is necessarily going to lead to heat flux variations across the system due to the smaller driving potential. So again, if the fluid is well stirred, as it were, and effectively homogeneous temperature-wise with respect to this heating time, then the driving potential between the jacket and the process side will decrease in proportionality to the local temperature in the jacket fluid. Here is the corresponding velocity. We get some pretty good impingement here where the jet comes in, kind of snakes out like some sort of neural network, snakes out, eventually recovers on the other side as mass continuity demands. But through these regions over here, we have a pretty depressed velocity, which isn't a bad thing, but it can inform our jacket side convective heat transfer coefficient, possibly. And so what we can do with this now is we can actually start to model like both the time evolution of the temperature inside the jacket and the corresponding time evolution of the temperature inside the fluid. Recognize that this is the whole thing. Like we're predicting the time evolution of the temperature at a probe inside this vessel as a function of the flow rate of the oil going through the jacket and thermophysical properties. That might be I'd say jacket topology and thermophysical properties of the fluid. That's pretty cool. I want to emphasize we do need to use our semi-empirical boundary layer theory model, which I think I've spoken about at length and ad nauseum. And we do need to specify, again, some sort of wall model, some sort of laminar wall model. Those are easy for the convective heat transfer inside the jacket. So there is some subgrid modeling. And I don't mean to dismiss that, but the point is it's not being it's very well validated based on what I've been speaking to at length today. So what's neat about this is I can see how the temperature is varying in and across the vessel as a function of these foundational operating conditions. Okay, we can see, for example, what the actual process side convective heat transfer coefficient will be, as I'll play this a bunch of times, as a function of the EDR. Remember, this H is a function of the fluid mechanics and the EDR and the fluid properties adjacent to the wall. So here we're seeing where the trailing vortex impinges, lots of EDR and lots of H. Up near the sidewalls, not so much, right? Not so much. So you can see why this jacket's kind of well designed. You get a lot of hot oil hitting where the EDR is highest, as it were, to get energy into the wall. These SPX engineers are good. Give them a call. But to be short near the top of the vessel, in fact, you can even see the free surface here. Like there's no conduction there. Although there's jacket oil there, there's nothing in which the temperature can conduct. So this is the local convective heat transfer coefficient. We can integrate this over the entire surface to get a system level value, of course, but we can also see the special variations and get some clues into what thermal stresses we might see. Here's the temperature of the shell. So we're seeing some conductive effects as well. Remember, there's no oil being run to the bottom of the tank. So then the only reason why the shell is warming up is because there's conduction into it. We model that in M-Star. That's not convection. That's just conduction, but nonetheless is in the code. So here I'm seeing this shell gradually get warmer and warmer and warmer and warmer as this heating oil heats it up. Okay, so it's kind of cool to see this evolution of the temperature profile inside the shell, as you see this competition between heat conduction from the oil, convection from the hot oil and the cooling off of that hot oil as it moves through it, conduction through the shell, convection into the fluid, stirring of that temperature to predict the spatial variation temperature profile. It's just magnificent to me to be able to see this entire problem wrapped up into one, right? We can see the competing transport physics. We can easily sample the effects of, say, operating conditions, operating topology, shell characteristics, heat oil characteristics, plumbing characteristics, and have one model to rule them all. And that's the promise, as I meant to say, of these GPU-based computing paradigms, okay? It allows us not just to run a correlation 500 times faster. It allows us to attack problems at this first principles approach, which allows us to couple disparate length and timescales in ways that were just previously inaccessible. And again, we can compare this immediately to simulation. Here are I've non-dimensionalized things to keep things kind of, above the board. But here's kind of the point, is that we can measure at the probe what the time evolution of the temperature will be, as it were. And that's just the probe in the water, below the surface, measuring how quickly the temperature is converging towards a steady state value. We can get the same thing out of the simulation. Yeah, there's a bit of there's a difference here. There probably is some error or uncertainty in our models, right? We're going to have 15% uncertainty, as you would in a correlation giving following or whatnot. But the real headline is this. First principles model reliably predicts several hour heating profile as well as the associated heating time constant. That's a long headline. And I think being able to do that with no retuning, with no parameter tweaking across a vessel of this scale and industrial size, that's pretty cool. And we can see here the approach is surprisingly robust. So if we compare the predicted, I can extract a tau. This is just first order. I can extract a tau from this. I can extract a tau. And so if I compare just my taus between the measured versus predicted, I'm consistently within, I'd say somewhere between 6 and 19% of what was measured experimentally. Interestingly, I'm systematically below, which says that I may have, it could be an experimental thing or it could be a simulation thing. It's obviously a simulation thing, but it could be some sort of something we're not accounting for in terms of either our fluid property. But either way, the headline is that we're nailing it, right? With one semi-empirical model at industrial scale, using just operating conditions to predict the response of a vessel, as well as temperature variations within it. Okay, let's wrap it up. It's pretty cool. It's pretty neat to be able to predict these transport physics using such a generalized approach that appeals nothing more than operating conditions. Okay, we don't have to use a system-specific correlation to develop correlation-like accuracy. The approaches are surprisingly general. Okay, and I showed that in the previous slide: tube bundles, pipes, agitated vessels, heating coils, etc. It's neat to see it work across a wide range of scales, and it's not totally surprising because the boundary layer hypothesis works, right? Like it's true across these scales. So it's not surprising to me that this works across scales as well. Likewise, it makes sense to me that all the fluid needs to know in order to transmit thermal energy in exchange with the wall is contained inside that small region of fluid. It doesn't need to look over its shoulder to figure out what the Reynolds number of the impeller was. It doesn't need to look down at the bottom to see what type of dish bottom tank, as it were. But to be sure, we can use this generalized approach to handle a wide variety of systems because we're appealing to the transport physics at the level of the transport carrier, as it were. These higher fidelity models mean simpler models. Like I said, I've used that same semi-empirical theory for everything. That's interesting. And I know many of you know that in a lot of simulations, we can be guilty of correlation hunting in an effort to find a correlation that gives us a good result. With here, we've tied our hands behind our back, as it were, and are only using semi-empirical theory to predict a pretty general result. And these results corroborate very well with both first principles predictions and measured data. Said again, we can put the probe in the vessel. We can pump the oil through the jacket and reproduce the response times, as well as the spatial variations across the vessel, as well as the temperatures, the possible sources of thermal fatigue and stress inside the jacket. There is a lot we can get out of these models. Guys, thank you for joining us. Appreciate you being here. As always, I'm like an ideal gas, and I fill the volume I'm given, and I've filled this time up to 10:58. But we do have a couple time. We have like 1 minute for questions. But yeah, thank you so much for engagement. Reach out if you have questions. All these files, except for some of the proprietary ones, I'm happy to share with you. You can run them in M-Star yourself and validate what I'm claiming here. But yeah, thank you again. I'm happy to take any questions here or later on in follow-up discussions.